Howdy, I'm Jarvis Sittel. Um, I apologize for a lack of camera. I don't have a working webcam currently. I thought I did. I pulled it out and it's broken, and um, so I apologize for that. Anyway, I'm here today to present my final project report for 5550. This project was pretty interesting because we essentially were creating a CAPTCHA beater, which I thought was fun. Um, Really, what it is a model that can utilize CFAR10 to identify images and what is in them. The data set is quite complicated. It uses 32 by 32 color images, which can be quite difficult for a lot of different models to handle. CNNs are particularly good at this, as they are capable of handling these kinds of unstructured data. I apologize for any stuttering. I'm not very good at presentations, and so I hope you have a little leniency. But working with CFAR 10 has been very enjoyable and very complicated. I went into it without a whole lot of experience working with these kinds of unstructured data sets, and it came up numerous times throughout my process of building the model and testing it and attempting to improve it. I made a lot of passes at trying to improve this model, and as we'll see later, it had varying results. Though through my online research, what I will say is that this was apparently a very useful and important data set for data scientists to utilize. I found a lot of people who often got stuck at certain points using it, but learned a lot and developed a lot through using this data set, and I found that very interesting. This project was really important to kind of learn how to optimize and improve accuracy for a data set like this. I'd only really worked with structured data prior, and so I found it quite difficult, as I've said. Here's my report. We're going to be going over this together. I gave a bit of an introduction just now. These two are obviously a student should not use Keras, but should use TensorFlow, as was discussed, and I put these here just to answer the question that was on the instructions. So going on to part two, where we chose a data set and talked about it. I personally chose this data set from downward in Nordby, and it's essentially a data set of acoustic aircraft audio clips. They're very ambient. There are two sets of them. There's the 0 set and the 1 set. 1 is for those with the audio, and 0 is for those without aircraft clips. The data set was available from the National Institute of Allergy and Infectious Diseases. I'm not entirely sure why this government entity was providing a data set about aircraft noises, but they were. One moment, I'm going to take a sip of water. There were a total of 1,270 audio files, 625 in the 0 and 1270 in the 0 and 625 in the folder with the airplane noises. They were labeled separately to indicate whether or not they had airplane noises. They were using a hex system, which I thought was quite interesting. Each file had its own hex code associated with it for easy, to easily find them. And then all of the ones without were just labeled 00000. It gives a lot of the metadata set that had all of the information about the images was really interesting. It has a lot of different information here. Actually, I'll just pull it up and show it. Probably better to give an example. I apologize for the delay. Here we are. This is the data set. They had the hex ID, so you could easily locate the audio file you were trying to look for. They also had, the airframe, the brand, the manufacturer, model, the engine type, all of this information just so you could essentially train a model to identify the aircraft just based off a short audio clip of 8 to 10 seconds. It was very, very interesting, very impressive. Yeah. The labeling and formatting of the data makes it perfect for machine learning, really. It's all super well laid out and super easily accessible and organized, and a machine learning algorithm would do a really good job of parsing through the data, and I found it very impressive. It's a very cool data set, and I would like to utilize it some days. On to part 3, which is just about downloading the data set from Canvas and uploading it to Google Drive. Here's a little image of me doing that. Yippee. We did it. Part 4. During my trial and error of getting the model to work, I had to run it a lot of times, I'll be honest. It was a really big process. I really struggled to fill in the blanks on the sheet of the instructions. I had a lot of class issues, or not a lot of class issues. I hadn't had to do something like this before. It was very different from the other models I'd trained, using Keras or doing linear regression, using these kind of systems that automatically kind of run the models for you, or build the models. So trying to get the data types right, especially since everything needed to be in float 32, I wound up having to Google it and read some Stack Overflow, but we got through it. It took me well over an hour to run each time, though, which was really frustrating because I would sometimes have crashes in the code close to halfway or 3/4 through, and it took over half an hour to run. It was crazy. And I believe that this was due to the complexity of the model, or really the data set. The batch size of 100 is quite a large set for 5,000 steps. I should have lowered the batch size or the step count while I was testing. I realized that in hindsight. Hindsight's 2020. But I managed to get an accuracy of 66.3% on my first run for the final, which was a pretty significant change from the 35.3% that I started with. Basically, it ran from 35.3 to 66.3. I have the data set here of all of the different versions. A bit of a spoiler, I suppose, but 35% to 66%, which I found very, very strange. I've run a lot of models using, as I was talking about earlier, programs that build them for you, or even in this class, I've run quite a few models, and this was by far and away the largest increase I had seen, which to me meant that this starting value was really bad because the model was probably not robust or complicated enough to handle the complexity of the data set right off the bat. The runtime was also pretty brutal and likely meant that there was that added to the complexity that I believe there was. But yeah, this is me. We're talking about the coding being really problematic for me. The batching also took a lot of time to get working. I did not entirely comprehend what we needed to do. Watching the lecture videos was helpful, but it definitely took some time. As for the makeup of the model, it is 2 conv layers, 2 pooling layers, 3 ReLU layers, a fully connected layer, a flattened layer, a dropout layer, and an output layer. It's a lot of layers. It's a very complicated, or it's not a very complicated model, not nearly robust enough for this data set in my opinion, especially looking at the numbers I found online. I mention it later on in the report, but I found a lot of people who were managing to hit significantly higher percentages than I was, 80, 90%. But I decided to just only, something I mentioned later on in the report that I am going to bring up now is I spent a lot of time working on this and looking at this and mulling over it over and over and over again. And I just wanted to make sure I didn't use any code or any ideas that I couldn't come up with myself. The idea of a final is to test yourself on your own merit. And so, while my results may have not been fantastic, I did want to make sure I only use code and ideas that I came up with myself. Anyway, here I talk about the difference between the MNIST model versus the CFAR10 model. Looking at the two, the MNIST model was 60% more accurate from the start, and by the end it still managed a 30% lead, which I think is still indicative of this data set being really complex for the model that I have built, because the only real difference here, as most of the code that I worked with in the missing sections was code that I copied over from the MNIST document and edited. That really means is the only difference was the complexity of the data. The color and the larger file size, I'm sure, contributed a ton to the runtime and the discrepancy in accuracy. Right. And so I also think the goal of the model was a lot harder. When I was looking at the images in the C4 dataset and comparing it to that of the MNIST model, something else that stuck out to me was how different the objective of the model was. The MNIST model was only having to determine what the digit was, which is a much simpler, much easier task than determining what is the object in an image, because objects are wildly different from case to case. Like, two dogs may not look anything alike. And there's a lot of background noise, and the color makes it a lot harder. So I really think that almost all of this difference comes from the lack of this model's capability of handling the more difficult task as well as the more complicated data. It's probably not breaking down the data very well. It's probably not like determining the object in the well, obviously it's not. That would raise the percent. But right. Anyway, let's move on to part 6. Part 6 is my proposition to fix the model's percentage, to try and improve it, to try and come up with something that makes it a little better. I proposed that a change to the learning rate to 0.0005% from 0.001 might help. From what I could tell, this would kind of help it in towards the end. My model would really plateau very, very hard. Let's go ahead and take a look, actually. It would plateau almost immediately. Like, we would go up 30% in the first 2,000 steps, and then would essentially not go up at all for the next 3,000. And so I was hoping that lowering the learning rate a little bit would allow for this data set to basically continue to correct itself as time went on. But I also I lost my tab. There we go. I also spent some time with adjusting the batch size. I wanted it to be a multiple of 4. So I just decided to bump it up to 128 because in my testing to get the model working the first time, I tried 64, 32, 96, and everything under 100 kind of reduced the accuracy. So I thought maybe bumping it up a little bit would help. Oftentimes bumping it up too much can either make it run way too long, which was already an issue for me, or it can kind of have a reverse effect. So I only bumped it up a little bit. And then I also lowered the dropout rate to 0.25 to try and help with underfitting. When I was looking online, a lot of things were talking about ways to help with overfitting, but I couldn't come up with anything on my own, and I didn't want to copy somebody else's code. So I decided to do this to try and help with underfitting, see if maybe it just wasn't trying enough things to improve the rate. But in the end, I'll be honest, it wasn't a whole lot of help. I spent a lot of time looking and trying to find a solution to this plateau, but as is very clear here, it didn't help. We started 6% higher from the beginning, which I took as a great sign, but we still hit that plateau about 2,000 in, honestly a little earlier this time, but we hit at about 2,000, we hit 6.6, or 66%, and proceeded to not change at all, which I think is really indicative of probably overfitting. I thought about it a lot. I saw online that L2 regulation may help, or augmentation of the images, but I couldn't think of a really great way to do that. I don't know enough about TensorFlow. I'm sure that if I'd thought a little bit harder, I could have found it, but I didn't want to go back and implement those things that I found online because, again, it didn't feel right for my final. That being said, we can move on to my conclusion. I have to say that working with data sets like images is difficult. It really is. It's really difficult for me personally, as somebody who likes to stare at spreadsheets. That's what I got into data analytics for. I love staring at spreadsheets. It's a very personal thing for me. I do a lot of spreadsheet work on my own. It's just kind of how I have fun. Here's my album bracket. This is something I've been doing, and I made a bot that predicts information for that. That's just my free time. I love numbers on a spreadsheet. And so working with audio and images has been really hard for me because it's hard to visualize it. I can't pull up a graph. I can't chart it over time. I don't really understand where my model is going wrong because I don't understand the data that well myself. And I think that is really something that I found interesting working with this, is something I'd like to improve on. But I'm a little ashamed that I didn't have better ideas to build a better model. I went into this very confident that I'd be able to improve it, and I was not able to. I write here, obviously, that these exact things. It's very difficult for me, and I'm interested in you, the professor, who I assume is listening to this. I'm interested in your takes on what I did. I'm very confident that what I did was at least a little bit helpful. My percentages did go up, especially from the beginning. And I'd really like to hear whether or not you believe that these changes were of sound mind, or if I was completely off base. I found it very interesting to work with this data set because it was something I'd never done. It was kind of out of my comfort zone. But especially looking at other people's online and seeing those 80 and 90% accuracy with a CNN on the CFAR10 data set made me feel like I was kind of messing up somewhere. And I say here that the problems with my model is that it's probably not robust enough, not complicated enough, and I do believe that. I don't think it's deep enough. I think that more layers probably would have helped. I'm going to dedicate a little bit of time towards the end of this video, this report, to talking about why my model didn't work, because I want to hear your thoughts and get feedback and see if maybe I'm kind of off base or if I'm on base, because I want to understand this model more than I do now. And I'm hopeful that through the grading process, I can get a little bit of feedback. But I think maybe I didn't add more layers because when I tweaked my model last time for the the MNIST model, I added more layers then, and it didn't really help. I added another set of conv layers and another flattening layer, or another pooling layer, sorry. And it actually didn't seem to do anything. If anything, it kind of hurt it. And so I didn't want to do that here because I didn't want to risk lowering my accuracy even further, and because the runtime was prohibitive enough that it made it difficult to try new things. So I wanted to know if, like, what you would have done. Was more conv layers the answer? Was my learning rate too high? Is there no way to achieve higher accuracy without implementing other things like regularization or augmentation? Because data augmentation, changing the images a little bit to reduce overfitting, makes sense in theory, but I didn't really understand how that would translate to the model. I'm sorry if I'm rambling a little bit. These conclusions are just things that I wanted to talk about. And I didn't write them here because otherwise this paper would be like 30 pages long. I also included the data set here. I guess I could have scrolled down to that instead of tapping out. But is the data augmentation useful in this case? Because rotating or changing the images feels like, yes, it may help it diagnose what is in the center because it'll less be looking for patterns in color or brightness to determine what something is. But I also was worried that it might, well, mostly because I didn't know how to make edits to the images like that. And I wanted to know, from your perspective, if that makes sense. Yeah. Well, I appreciate you listening. I haven't quite hit the time yet, but I don't really know what else to say. I will maybe take one more pass at this and say I feel like this data set would be really interesting to do kind of the similar thing with, and I hope that I get around to that. Yeah. Thank you.